Hey, Greg, just in the interest of time, I'm going to go ahead and start the recording now. So we have
Okay.
at the top of the hour.
Perfect.
So whenever you're ready.
I'm ready.
All right, let's do it.
Okay. Well, first of all, I want to thank everyone for joining, especially those of us on the Pacific Coast time zone who are up at 6 a.m. But more generally, I just really appreciate everyone's engagement and involvement. Thank you very much for this opportunity to go over some of this material. There are some people who have joined sort of at the last minute here, and we did have a session earlier, about a month ago, where people introduced themselves. They said who are they, where they're from, what brought them here, and what is their aim. So for those who haven't already done that session, so that would be Nate and Kenny and Ryan and Jacob. If you could please just very briefly, very quickly, just introduce yourselves as I suggested, I would appreciate it.
Sure, I can go first. That's cool. Hey, everyone, I'm Nate. Super excited to be here. I met Greg through some blockchain stuff. I help out with some research at the Ethereum Foundation. And I'm here essentially because, I understand about one millionth of what I wish I did. And I'm super excited to kind of learn from Greg and maybe hopefully be able to understand at least half the things he says one day. But really, yeah, just here to learn and super excited by the material.
And where are you from?
I'm from Philadelphia.
See. And why don't you tag one of the other people who hasn't gone?
Was it Kenny? Kenny was one of the other people. Tagging Kenny.
Yeah. Thanks, yeah, so my name's Kenny. I actually work for the co-op doing operations work, and I've been very interested in the underpinnings of the mathematics that drive the platform in general, mostly because that's what inspired me in the first place. And so my aim in this whole endeavor is to get the whole thing off the ground, and then as soon as that platform is up and running and sort of the computational backbone of hopefully the entire planet, I want to understand that at a very fundamental level. And in order to do that, you got to start the math. So that's who I am, and that's where I'm coming from. And I am located in West Seattle.
Sweet.
Who was one of the others that hasn't?
So there was Ryan and Jacob.
Let's go with Jacob next.
Thanks, Kenny. Hey, everyone. I'm Jacob. I'm from New York, and I'm here because I want to follow my intuition with how, elegant the idea of using Rolang and RoCalc and concurrency to model the blockchain sounds, but I'm a total novice. I don't know a lot of math or a lot of programming, so I'm excited to learn and just to be here. I'll tag Ryan.
Ray?
Yes.
All right. Hey, I'm dealing with a tropical storm situation here in Florida. But I'm back and forth to New York and Estonia, and I am very interested in getting the software industry away from Lambda calculus. And that's kind of how I stumbled into Rolang. Actually came out of the AI space, but I see a lot of parallels. I've written up a lot of stuff on Medium, kind of babblings about just my thoughts. Some of the write-ups are more organized than others. So I'm very excited, though, to be involved in this kind of work. And it's very refreshing to see some of the academic science come back to the industry, because the industry's kind of been a bit of an intellectual wasteland, at least for the past decade or two. In fact, I got out of the industry because I got kind of disillusioned with the whole thing. So very excited to see all this kind of make some progress again. So So, and I used to do academic research back in the day, but you know, that was a long time ago. So, all right. Hello, everyone.
Hi there. Thanks, everyone. So I'm going to go ahead and jump right into the material. I'm really looking forward to talking about that stuff. That's where I get really excited. So I'm going to go ahead and screen share now. And let me make sure everyone can see this.
Yeah, I think you're good.
Okay. Let me just quickly. Okay. So this is part of the Arching education series. And today's agenda, as we mentioned in the email that sort of had the course syllabus, we're going to talk about the presentation of the calculus and what goes into that. And I'm gonna, you know, there's some major elements, the three main pieces of this. And I want to give a little bit of the relationship of this presentation to other mathematical structures and to computational structures. And also want to talk a little bit about how these kinds of presentations set up a structure-function relationship, which is a very biological idea. You know, often we look at critters in terms of how their structure, you know, what we observe in their structure is related to the roles and functions that they serve in relationship to other organisms. And it turns out that this kind of thing shows up quite strongly when we dive into the presentation of calculus. So I want to talk a little bit about that at the end. The first thing I want to do, though, is to, that's weird. There we go. There we go. Is to dive into what is a grammar. And I've given a couple of examples of grammars. These grammars are they're basically living inside a presentation called BNF. And I'm just curious, how many people are familiar with the Bacchus-Nauer form or BNF grammars?
Small bit.
Mediumly. I've read a few, haven't written one.
Okay, so BNF grammars are a tool of choice if you're writing a parser. They're organized. There's lots and lots of details about these kinds of things that we could go into, but I'm not going to go into all of those details. Essentially, they're of the same. So there's a class of computational models known as the Chomsky hierarchy. And essentially, BNF grammars are equivalent to what are called context-free grammars. There's some subtleties there, which I won't go into. But it gives us a way to describe structural relationships, how to build data types. And we'll talk about that in more concrete terms in a minute. But this was picked up by the theoretical computer science community that is interested in sort of building out and investigating particular models of computation. So this part of it describes sort of the structure of our domain of discourse, the things that we're going to use to compute with, and how they're built. And it's also quite related to a couple of other sort of mathematical entities, which we will dive into in a bit more detail as we go forward. Not so much for universal algebra, but certainly from a category theoretic perspective. So in universal algebra, we are often also interested in these kinds of structural relationships, and they're typically written down generatively in the same way that grammars can be thought of as generative. So we'll look at that generation with a few examples here. So the first example is an example of a grammar for the Lambda calculus. And the second example is an example of a grammar for the row calculus. And there are lots of other calculi, and I'm going to invite people to write down grammatical descriptions for other calculi as we go deeper into this. But I'll give you just a kind of naive or intuitive interpretation of what the symbols mean. Please be aware that I'm using a somewhat idiosyncratic form, which is multi-headed, and I'll explain that in just a moment. It's not that it's completely my own style, but it's a style that is more, there are fewer people who use this style, but it is used by people like Luis Caires and other researchers in the field. So it's well understood, it has a clear mathematical foundation, and we'll talk a little bit about the subtleties in just a minute. So the way to read this is a grammar for the Lambda calculus. And what it says is that Lambda terms, which we will range over using the symbols capital M and capital N, are of the form, so that this funny : equals sign, it means are of the form. And then there are three choices, and this vertical bar with the space on either side is a sort of like an option or a menu. The first option is a variable mention. So a Lambda term can simply be the mention of a variable. Another kind of Lambda term is recursively built. So assuming I had a Lambda term in, then I could make a new Lambda term by prefixing onto M Lambda x dot, and this represents abstraction. So it's M in which x is a variable which could later be supplied. And then the third and final option is application. So this represents the application of some Lambda term to another Lambda term. Now this is meaningful because the Lambda calculus is modeling a notion of function. So we expect Lambda terms to be like functions, and oddly, they're also like values. So the Lambda calculus is the first calculus where we get kind of a first class notion of function or computation. So we can pass functions around as if they were values. And that's a very powerful idea, and one of the reasons why the Lambda calculus and many computational languages or programming languages built on top of it have such power and appeal, because functions are first-class entities and can be passed around and returned as results. So that's the Lambda calculus grammar. Before I go on, I want to stop and check and see if everyone has understood what I've said, or if you have any questions.
Greg, could you explain so Lambda x?
We can't hear you, brother.
Go ahead, Kenny.
Can you hear
Say
me?
again?
Can you hear
Yeah.
me? Yeah. So Lambda x, can you explain what the operation is? There any operation, or what's the relationship between Lambda and x?
So what Lambda x is doing is it's binding x in M. So it's turning M into a function. For example, let's say that M is just x, the mention of the variable x. Now, without any binding, that would essentially be a kind of compiler error. We're referring to a variable that has no binding and no value. So if we try to evaluate that term, it would be like, well, I don't know, what is x? You didn't tell me. But as soon as we apply lambda x dot to x, so if we say, or prefix lambda x dot to x, we get a function. So that function can be used in the application position on the third option. So if we applied lambda x dot x to something, then we will go through a computational step. And that step, which we'll get into a little bit later, but just to help intuitions, we'll substitute whatever we applied, lambda x dot x, we'll substitute x for whatever we applied it to. So in this case, let's say we applied it to n. Then when we do that step, we substitute n for x in the term x. So that means we get back n. So whenever we apply lambda x dot x to some term n, we get n back. So this is the identity function. Does that make sense, Kenny?
I'll keep noodling on it, but
okay, we'll come back. It's going to be clearer in symbols in just a few minutes. But literally, what it's doing is lambda is making a function. It's making an anonymous function. And there's a close relationship between the lambda and the for comprehension in row calculus. So, any other questions about this grammar? In some sense, one thing you can do, and what is common to do in mathematics, is you can just treat it as a formal game. So in that sense, don't worry about what these things mean. Just know that this is setting up the rules of a game. And the game is this term a legal lambda term? So for example, we know, and we can play this game either generatively, or we can play it in terms of this, so that would be generate another lambda term for me, or generate the next lambda term in the infinite stream of lambda terms. Alternatively, we can say, I'm going to hand you a term and you tell me whether or not it is a legal lambda term. So let's try and do some calculation with the grammar. So if x is the smallest, and by the way, there's already something that's poking out in this kind of presentation of the lambda calculus, which is that it's not just x, it's x's and y's and z's. And you'll notice there's nothing here that tells us where x's come from. And we rectify that in the next grammar. But just for now, let's say that we've got an x, okay? Then I can form the next term. There. That x is the smallest. This is what gets us off the ground, right? These two terms mention m and n. And so without an m and n in our hands, we can't utilize these different productions. This is the only production, the only option that doesn't depend upon m and n. So in order to make one of these, I have to, sort of from scratch, I have to either have had one or I appeal to something that doesn't depend on m and n. So this is really sort of like the next or the smallest lambda term. Can someone give me another smallest lambda term?
X space X.
Right. If we apply X to X, or more generally, if I apply X to Y, right? These are also the next smallest lambda terms. That's exactly right. And so this represents the application of X to itself. And this represents the application of X to some term, some variable mentioned Y. Right? So, and now with these, we can form other terms, right? So for example, I can form lambda x dot x and apply, I'm just going to put it in parens so people know where the scope is, and apply that to, let us say, for example, y. That's another term. You don't have to know the meaning of that. You don't have to understand that it has a computational interpretation. We're literally just playing a formal game and making these funny sentences or these funny little data structures. And this grammar tells us when a sentence that's built using x's and lambdas and applications is legal. Does that make sense to people? Are people sort of following along?
So, Greg, when it says grammar, it almost literally means grammar.
Yes, that's exactly why that word is. Yes, that's it. It's the legal sentences in your language.
In the calculus, is there really only one original input like X and everything comes from one thing?
So that's a very good question. So really, X is a kind of meta variable. And this is very confusing in this style of presentation, which we'll address in the next one. Really, this is X or Y or Z or U or T or whatever your set of variables is. So whatever you have picked as your set of variables, the set of legal identifiers, then you can use that as a mention, or you can use that in an abstraction. So that's why I started using Y's, right? And so, for example, I could do something like this. Lambda y dot lambda x applied to y and that whole thing applied to, get this right, that whole thing applied to.
Sorry, Greg, can I
Yes.
interrupt you for a minute? Hi, I'm Andreas.
Yes.
I was thinking about, I see what point you're trying to make here, and some interesting thing I noticed lately on Twitter, people were explaining this stuff, but instead of using X and Y, they were using Unicode emojis.
Sure, we could do that as well.
Yeah, you can put in cats and dogs or something like that. And
Yeah.
so people get the abstract notion of this thing, not just the letter X or some, yeah. So
Yeah.
maybe I don't know, maybe cats
Yeah.
and dogs face help a little bit here, maybe, I don't know.
Sure, you can absolutely do that. And that's a similar idea is on the next slide. Yeah, that's well observed. It's a very good notion. So do people get this idea of that we can just build up these sentences or objects or expressions, and we can either generate all of the legal expressions that come from a grammar, or we can, given a sentence or an expression, we can check to see that it is in fact legal. So here's an example. Can someone, or let me put it the other way, can someone give me an example of something that is not legal?
Lambda x dot.
Right.
And
Lambda x dot is not legal. That's correct. Very good. All right, so these are all some examples, and now let's move on a little bit and talk about another example. So in this one, we're building terms using, and that we're ranging over those terms using P and Q. So P can, either P or Q can stand for a term. And we use that, we need this to be able to form recursion. So the first one is very much like, so it looks like we have some chats. Take a look and see the screen. Okay, cool. All right. So the first one in the menu of options is a special character called 0. So a legal term, which we range over with P and Q, is of the form either 0. So this is just like a special term that we've picked, or it's what's called a for comprehension, right? So for y from x and then p. So if you had a legal term p, you could form a new one with this for comprehension prefix. And this is very, very much like Lambda. Or you can form, if you had a legal term q, you could form a new term by saying x bang and then putting q in parens next to that. Or if you had two legal terms, P and Q, you can form a new legal term, P par Q. And then your final option is if you have an X, whatever that is, you can do a star X. And now we tell you what X's and Y's are. So X's and Y's are formed if you have a legal term P, then you can make an X and a Y by putting the @ sign in front of it. So that's your grammar. And notice that this is now more complete than the Lambda calculus, at least this presentation. It's more complete because there are no symbols here, with the exception of 0, that are not well defined. And here we've chosen 0 as a special character. It's provided as a special character. Here, X is actually really to be interpreted as a meta symbol, a range of different possible things, like cats and dogs, or emojis, or other kinds of things. Here, this is not standing in for a whole infinite supply of things. It's really just one thing. And that's kind of important because the whole rest of this recursive structure builds off of this one thing. So for example, if I what's the first off the ground process, or the first off the ground term in this grammar? That's the 0. That is the beginning, right? We get everything from there. So what's the next smallest process we can build?
Star 0, I guess.
That's a great try, but it's not legal. Why is it not legal?
X is constructed differently than P and Q.
Right. So one way to think about it is in terms of types. So X is of type, X is one of these types, and it's not a P. So I can't apply a star to a P directly. There's nothing in this grammar that allows me to apply a star to a P directly. I can only apply a star to X's. In order to make an X, I have to put an @ sign in front of a P. So why don't we begin there? What's the first smallest x and y, x or y?
At 0.
At 0. That's exactly right. That's the very first name. So this is the first process, and that's the first name. And now that we have at least one name and one process, we can form some new processes. What's the next? What's one of the smallest processes that we can now form?
Star at 0.
Yes, correct. What's another one?
0 par at 0.
Yeah, that's another one. That's a good one. 0 par. Now at 0 or
Star, yeah, star at 0.
star at 0. There we go. That's correct. Right. Here's another one. At 0, bang, 0. Does everyone agree that that's a legal process? Sweet. Here's another one. 4 at 0. From at 0, 0. Does everyone agree? And now we can form names by making, by putting stars in front of all the things that are processes. So for example, here's a process. I'm gonna put some parens around it, and oops. And now I've got a new name. So before I only had this name. Now I've got this name as well. And similarly, I can make another name. There, that's a name. So that gives us some examples. You might notice something funny about this. There are no variables in here. In fact, this is a kind of machine code. You can directly encode processes in, or terms in this calculus, in this grammar, to be more precise, as numbers, if you so desired, which is a little bit different than the Lambda calculus, because Lambda calculus starts with an infinite supply of variables. We don't know what kind of things those could be. Those could be emojis, they could be pigeons, they could be dolphins, they could be planets. We don't know what they are.
Sorry, when you say each one of these could be encoded as a number, do you mean like, you know, we could go from any, we could make some function that maps any row calculus thing to a number?
Yes.
Okay, and so how does that relate to, like, you know, machine code? What's the relation?
So you can quickly you can basically give a binary representation for every row calculus term. And in fact, if you go to Akbar's Grasp repo, you will see several implementations of binary representations of row calculus terms in a machine for the row calculus.
Oh, cool.
A circuit for the row calculus. And you should be able to see this directly, just from what you're seeing. If you had some binary for the @ sign, and you had some binary for the star sign, and you had some binary for the par sign, and you had some binary for the bang and for the 4, you're done. Now you can see quickly how to recursively build up a binary number for this structure. So this is very different. It's a very different animal from this one. And pi calculus sits kind of in between this one and this one. But let's move on. We have a lot of material to cover, and we're already 34 minutes in. Okay, so hopefully everyone has a sense of what are the legal terms from for this grammar and what are the legal terms for this grammar. So now I'm going to unpack the Lambda calculus a little bit more. Let me go back into presentation mode. Can everyone see that?
Yep.
Okay, so these things, because as we've seen from our discussion, they're a little bit mysterious. And when we encounter something that's a little bit mysterious, sometimes we make mathematical models of these mysterious objects. So here's a little mathematical model that uses either just plain ordinary set theory with some recursion thrown in, or it uses category theory, depending on how you interpret these operations. So we're going to build a recursive set or a recursive object. And that object, M, is going to be parametric in some other thing, capital X. And that capital X is where we're supplying this set of little x's, or this collection of little x's. So M is parametric in the set of things that will become variables. So it could be X, capital X could be the set of all emojis, or capital X could be the set of all species of dolphin, etc. We don't know what it is, but we know that if you hand us one, then we can form this recursive structure here. And this recursive structure uses disjoint union in as a connective between three different sub terms or sub chunks, three different chunks of the set that we're building. And so that disjoint union corresponds exactly to the vertical bar. Okay? Does that make sense? Do people know what a disjoint union is? Awesome. Very good. Are people still there? Let me make sure that people are still there.
Yes, we are.
Yep.
All right. Does everybody know what the union of two sets is?
If you take one set and another set and put it together, then this is a union.
That's right. That's right. So if if you have the set A and you have the set B, then all of the elements of A and all of the elements of B make up the elements of A union B. Now, suppose I have the set X, Y, Z, and I have the set Y, Z, W. When I take the union of X, Y, Z with Y, Z, W, I get X, Y, Z, W. So I don't duplicate the overlap. Does that make sense?
Yeah.
Yeah.
Okay, good. Now, there's a way that we could keep them separate even while mixing them. So let's say that I'm going to, and here I'll do that very quickly here. I'll just type that in. Make it a separate page. So let's say I have one set, which is X, Y, Z. And I have another set, which is Y, Z, W. And we've just agreed that X union Y is equal to X, Y, Z, W. Now, unfortunately, that doesn't allow us to see the overlap. It mixes them, and we can't ever sort of, if I just presented you with X union Y, and I said it's X, Y, Z, W, you couldn't recover X and Y from that, because you wouldn't know how to partition this into the elements. Does that make sense?
Mm-hmm.
Okay, great. Notice that there's an operation. Notice that if I were to take the Cartesian product of X with the set 0, then this would give me, or let me do it the other way. I'll put the tag on the left-hand side. I'm going to take the set 0, and I am going to take the Cartesian product of that with X. So this is going to be all the pairs of the form 0, comma, X, where X is an element of the capital X. So 0, comma, Y, and 0, comma, Z. So, and notice that there are exactly the same number of elements here as there are here. And that's because there's only one element here. So I can kind of always recover my original set just by projecting out to the second element of the pair. Does that make sense? If I just take the second element of every pair, and I collect all those into a set, I get back my X. So this thing is isomorphic to that thing. I can, given an X, I can always form this. Given one of these, I can always recover X. So now I can also do this. I can do 1 Cartesian product with Y. And this is going to be just as before, 1, comma, Y, 1, comma, Z, and 1, comma, W. That makes, hopefully that's clear. And similarly, this is isomorphic to that. I can, from one of these, I can always construct one of these. From one of these, I can always recover one of these. Now notice what happens if I take the union. I'll put parens around this so it's clear. I get all of these. Together with all of these. Does that make sense? Did people see that?
Looks very spatial.
Okay, so now notice what happened. The overlapping things are disambiguated. They're distinguished because they have a tag. So the disjoint union is tagging the elements. So, and whenever we have multiple of these sums, we can just make additional tags. Like, you know, this could be tagged with 0, this could be tagged with 1, this could be tagged with 2, or this could be tagged with, you know, 0, 0, 0, 1, and 1, 0, for example. So the tagging is what allows us to disambiguate each of the different options. Now, if we interpret this in category theory, it's not so concrete. We're not necessarily saying this is sets. We're saying there's some operation that respects the meaning of tagging. Likewise, there's an operation product that respects the meaning of taking pairs. And now we can give a nice, crisp interpretation of our infinitary grammar. So either you have a tagged X so that you know it's a mention, or you have a tagged pair where you've got X in the first part and some MX in the second part, just like this. Or you have a tagged pair where you've got an MX in the first part and an MX in the second part. So that gives us a little model, a mathematical model of what this grammar means. Now that allows us to give a crisp computational interpretation in terms of code like Scala. In Scala, we would use the object-oriented features to model the features of the grammar. Things on the left-hand side of a production are called non-terminal symbols. Things that never appear on the left-hand side of a production are called terminal symbols. So all of our elements are effectively going to be an extension of an overarching trait or class. And we know that that thing is going to be parametric. It's a type that is parametric in another type, which is X. So if you hand us a type of variable, which we're calling X, then we can form a new type, which is a lambda term. Is that making sense? Is that connecting with people?
Yep.
Okay, good. So now we're going to form 3 classes, just like there are 3 options. In Scala, Scala gives us the notion of case class, which allows us to tag and disambiguate in the same way that this mathematical model tags the different options. Essentially, the tagging allows us to do pattern matching on the different forms. Here, the tags actually become the names of the classes. So where we had a 0 here and a 1 here and a 2 here, that 0 becomes mention, the 2 becomes abstraction, the 1 becomes abstraction, and the 2 becomes application. So the case class tagging in Scala corresponds to the kind of tagging we find in disjoint union. And now everything proceeds exactly as we see it both here and here. A mention, which is this thing, is going to contain an X, and that X is going to be of type X. So mention has to be parametric in X so that it can extend the trait MX. And it's going to contain exactly one thing, which is going to be of type X. Likewise, an application is parametric in X, but it contains 2 things. The variable for the abstraction, that's the lambda X here, which has to be of type X, and the body of the lambda abstraction, the M here, the term, which is going to be of type MX. And then finally, we have application. So I have an M and an N, and both of them are of type MX. Does that make sense?
Yep.
Good. Is there anyone who has any questions about this?
My only question, Greg, and just to make sure I got you right. So the plus is this union with tagging, right? Like on the second line.
Yes.
All right. Yeah. Here.
That's exactly right. Yes. And the plus corresponds to the case class construction in Scala.
Yeah. Thank you.
Yes. Go ahead.
You were talking about production. What are those?
So a production is really one of these things. So if we go back, this grammar has one production. This grammar has two productions. Is that clear?
Okay, gotcha. Thanks.
Sure.
If I-
Okay, go ahead.
So was the first example set theory and this is category theory, or am I not right?
So what I was saying is that you can use set theory to give a very concrete interpretation of this recursive equation here. So I can give a set theoretic interpretation of this object. This object is a kind of set. But I can also give a category theoretic interpretation, which means that I can be much more abstract than just sets, which allows me to cover a range of different possible models of this recursive equation. And that becomes important if I wanted to be able to realize this on different structures. Like suppose I wanted to see if I could interpret this structure in mathematical entities like groups or vector spaces. If vector spaces supported these operations, and they do, then I could form a vector space which modeled this recursive structure. And that might be useful and interesting. For example, if I have a computer that was really good with vectors, I might gain an advantage by interpreting this in terms of vector spaces. Does that make sense?
Yeah.
Okay. And please, folks, don't say it makes sense if it really doesn't. Don't really, really dig in, and don't let anything go. So I would like for people to help me write the recursive equation for this grammar here, and then to write the Scala code for this grammar here. So who wants to start?
I have a question.
Yeah, go ahead.
So before, for Lambda, we were like, this was parametric and in like capital X, which is like this set of, kind of unidentified object things. In here, is big X just zero, or some single element thing?
Excellent. I'm so glad you said that. So yes, let us begin with and just to be careful, just to be super careful, we won't call it X. Let's call it actually for the very first, to get off the ground, I'm going to let you know that we get to have a special symbol called 1, which turns out to be the set with one element, or it's the terminal or initial object in a particular category.
Cool.
Okay. So that's 1 corresponds to 0. Now, what comes next?
So do we not need P to still be parametric in the notion of name, but that notion of name is just the one that we're using below? Or we can remove that?
We don't, but I like your intuition. There's something that's going to happen. And what's going to happen is that we're going to have something for X. So give me the cases. Give me the cases, right? We're going to have a bunch of pluses, and what are on either side of those pluses?
So I guess the next thing we'll need is just some sort of process that gives us a name. So it'll be plus P.
Almost plus. So we would have P equals 1 plus P, but that's not quite right, right? We just literally, let's just read off the grammar. Let's just follow the grammar. Sorry. So plus, and what's the next case? We have an X and we have two X's and a P, yes? Okay, so as mathematicians, we have all kinds of creativity at our fingertips. So I'm just gonna pull an X out of the hat. I don't know where that X came from, but I'm gonna supply it later. So X, this X here is an X, and that Y there is an X. So I'm gonna call that X cross P. Does that make sense? I got some head nodding.
What does the cross mean?
The Cartesian, it's Cartesian product.
Ah, okay, yeah.
Okay, so I have another plus. What's the next case?
X cross Q or P. X cross P.
X cross P, exactly. Good. What's the next case?
P cross P.
Yes. And then what's the next case? Oops. It's the final case.
X.
It's just an X. That's exactly right. Now we can eliminate the X, right? We can eliminate the X because X is equal to
P.
Yes. So that's a funny one. So we have to be a little bit more careful than that. This would not result in if we substituted P for X here, we would not get what we want.
Do we somehow have to tag it with something? You know, maybe.
Yes, it's close, very close. I'm now going to do the recursion. This is called tying the recursive knot. So I first make this thing parametric in an X, and then I'm going to make a funny kind of I can do this in two ways. I can either use a fixed point operator and calculate mu x of px, or I can do it in a more traditional style. So I'll say rp is equal to p of rp. So now I put in the recursion, and that's how to tag the x's. And this gives us exactly that alternation between processes and names, between p's and x's. Does that make sense? This knot tying thing is very, very important. So if it doesn't make sense, we should take some time and get it. We have about 2 minutes left. We have a lot more material, which is fine, but we really should get this.
So
RP is just arbitrary, or does it have a meaning?
No, it's quite clear. We've said exact. This is just a symbol. I can just, instead of, let me just call it R. So it's clear. This is just a symbol, and now we're giving it its meaning. R is this P, which is parametric in X. I'm going to apply that to R. So this is a recursive equation. So here's a recursive equation. It's recursive in P of X. And here's another recursion, which is to set to, it's the fixed point of this recursion. So where it's you can think of it as a kind of double recursion. This thing will recurse on P of X, and here we're closing that up, right? We're getting rid of X by forcing by taking P of R, right? So R is P of R. So we find the recursive fixed point of this equation.
Okay. So is the goal here to essentially get rid of X?
You get rid of X, exactly.
I see.
Yeah. So we can write this in Scala, and we should. We're out of time now, but what I would like you to do is to give a shot between now and next Monday to write this thing in Scala. And it turns out it's quite tricky because of some constraints that Scala has. It's a little bit of a subtle problem. Alternatively, if you prefer, you can do Haskell, and I have solutions for this online if you're interested, or if you get stuck. I really encourage you all, but you now all have each other's emails, to discuss amongst each other. I think Jacob set up a Discord, and come up with a solution.
I also want to give a quick shout out that every Friday at 8 a.m. Seattle time, I'm doing like a discussion session thing, Arching Collaborative Learning. We're doing defining PyCalculus grammar and K-framework. And I was also hoping to use it as sort of a discussion section for these lectures. So
awesome.
If you're interested in that, I'll post a link in the chat, and then you can sign up for the email list and get updates.
Sweet. That's very good. Next time, we will finish that off, and then we'll look at structural equivalence. And probably, just to get a sense, how many people know what alpha equivalence is? Okay, so we'll have to take a detour through alpha equivalence, which is actually turns out to be important. And then we'll look again at structural equivalence, and then we'll look at operational semantics, and then we'll come back to this question of how this presentation differs from other mathematical presentations. Thank you so much.
Thanks, Greg.
Thanks, Greg.
This was awesome.
Hopefully this will. Yes. Ciao.
Thank you. Bye-bye.
Bye.
Thank you so